All right, so let's get started. And although I have these slides up here, who started with project 2 already? Or the right question, I guess, is who finished project 2? No, nobody. All right. Me asking these questions will help. Maybe one day you'll at least take a look at the instructions and stuff before you come into class. That's the hope. All right, but I'm not going to get started with those slides. What I'm going to get started is with this. So let's see. Who recognizes what I'm about to do? All right. Matt, want to come up and talk about your project 1 for 60 seconds? No more? So very brief, okay? So if you want to focus on what you did uni, what were some of the highlights that you had?
Mind if I?
Yeah, use the mouse and stuff.
I'm gonna put this up because it's way more interesting.
Yeah.
So what do you suggest focusing on?
What do you want to talk about?
So bullets flopping, invented in 1970. Yeah, I don't know. I was able to implement all 3 algorithms. 2.3, the more efficient algorithm for me personally was not more efficient, indicating that I was not, in fact, accessing memory contiguously. However, I had such a hard time. I basically spent all of my working time debugging various things, to the point where I did not have time to complete 2.3 and have a passable write-up. So I didn't. So part 3 for me did not work more efficiently, but did work. What I did take the time to do, however, was compare the runtimes of things and graph them. So you can see that the orange here is consistently, the orange being supposed to be more efficient, coherent version of the algorithm is consistently less efficient than scattered. But you can also see visually how much better things are, regardless of. I didn't have time to graph this, but I made a table, regardless of block size. So that was basically how I broke down. And that's probably 60 seconds.
Yeah. All right. Good job. Any questions? So Matt, when did you find out that your work efficient wasn't as fast? Whatever the fastest one. Sorry.
Yeah.
Was not fast because of memory.
That was mostly an assumption. I did not do sufficient profiling to confirm that with hard numbers, but given that the only difference in algorithm was shifting memory around, there was one extra sort, I think, that would not have explained the significant difference there.
All right. Yes. Yes, I do.
How many buffers did you have?
I used 2 extra buffers. I think it was 2 extra. And what I did was I ended up sorting, let's see, can't remember. I ended up effectively using one of the buffers to copy the order of the translation array, and then always had a copy of that whenever I would sort by it, so that I would end up with, because you obviously change both arrays when you do key sort. So I basically kept a copy of that at all times. And I knew that I would need more than 1 additional buffer because I would be sorting by the original, have a copy, and then need to sort by that copy as well. So I need a copy of that copy to sort by it again. If that answers your question.
Anybody else? All right, thanks, man. Good job. Right, next we have Tang. There you go. All right, come on.
What should I do?
Just talk about what you did unique in your project. What was interesting? What did you learn? Those kind of things.
Oh, okay.
You don't have to talk too much, just 60 seconds. How would you explain this to? If you met a friend that's not in 565, how would you explain it?
Okay. So in this project, I implemented the voice flocking algorithm. So this is the result for 10,000, and this is the result for 100,000, and finally I achieved the best result as this is a picture for the 10 million boys. Oh, it looks crazy, yeah. Okay, and then I did the performance analysis, and like this, it can be seen that the frame rate will drop significantly with the growing voice number, and without visualization, we will see that performance is a little bit improved. Okay, and then, but in my experiments, I see that even if we grow the block size for about 10, 22, 24, but it seems like there is almost no change, but just a little bit drop. Okay, then I tried to have the cell width as the max distance of each void, and I see that even if you need to check 27 neighbors at this time, but the performance indeed improved. And finally, I did the grid looping optimization, but I got a little confused since I'm not sure I did any effective change on this, since I noticed that the origin method checked the 8 neighbors, but with this optimization, I just check the neighbors which is within the max distance. I don't really sure this will make actually effects, but the result shows it indeed has a performance improvement. Yeah.
Thank you. Any questions? Good, man.
Yeah. It's my personal computer. It has this RTX 3070.
Do you have another question?
I guess I was curious how long you spent on your
7 hour.
How much time did you spend writing your readme?
Oh yeah. About 4 hours or 3 hours. I'm not sure.
I'm surprised you guys didn't spend 4 hours. Like, that's what you should be spending. Okay. So one really good readme, good screenshots. Are all of those real time, or did you speed them up?
What?
Is that captured real time, or did you speed them up in like a video editor?
Oh no. This is real time. Okay.
The other point I'll give you is, without checking, I think this is the first time I've seen somebody do a non-visualization benchmark in the class. So I think that is really good. You went out of the box, thought about something new, and did it. So good job there.
Okay, I think it will. Thanks to my GPU. Okay.
All right, thank you.
Okay, thank you.
And last we have Charles. Charles, you want to come up?
Right. All right. Hello, everyone. Yeah, sure. This is my project. It's a flocking simulation, just as everybody else. I think one of the highlights that I got is I was able to simulate like 12 million points in a single simulation, probably because of my beefy gaming GPU. I got a 3080 here. Yeah, it's really hard to get. Yeah, but I would manage to get one just in time. So for the first pictures, I was really using like a higher value of DT to speed up the simulation to see all 12 million boys interacting with each other. And for the second picture, there's a smaller DT to see the fine individual movements between all the boys. I think the second one is really cool. It kind of looks like a nebula, some sort of that, right? And for the performance analysis part, I did like 3 approaches, just as anybody else: naive, uniform, and coherent approach. And the conclusion I got is that there is approximately 10 times, 10 times efficiency improvement in terms of the number of voids a method can handle per step, going from naive to coherent uniform grid approach. So the naive can handle like thousands of voids, but the coherent grid approach can handle millions. So that's like 10 times going from naive to uniform to coherent. Yeah, the reasons is obvious. We call a lot of neighbor checks by checking at most cells. We also eliminated one level of interaction when accessing the velocity and position arrays. And secondly, I also compared the block size versus FPS as well. So I think I got something wrong about this graph because I don't think 1024 can give us better performance in my machine. Yeah, that doesn't make any sense at all. Because last time I checked, my GPU has like 5036. The max thread allowed on the SM is 5036. So 1024 shouldn't be the most efficient one because some threads are idle in every single SM, right? Yeah, I think that's it.
Thank you.
Yes, they are. Second picture is inside the cube as well, but I zoom in inside the cube to see the movements better.
That reminds me of a small simulation I did for 563 when I was a student. I mean, it wasn't like that, but my simulation was similar. I mean, when I had 2 gases come, one from down, one from bottom. Looks really cool. Also a reminder that was real life. It would be a really cool Instagram place. Anything else? Yeah.
So 2 questions. One, if this is the inside of the cube, it seems like a lot of the voids are up against the edges of like.
Yeah, that's after I wait for a period of time, waiting for all the boys to settle. And this is the effect I got.
I wonder why the voids settle towards the edge of the cube.
Yeah, I think this is because the DT I set is too small. If you wait enough time, I think these boys won't be just hanging out there. They will move up and down, left or right.
And then the second question I have is on the graphs, you have a line, a green line.
Oh, yes. This is actually the metrics I used when I was playing video games. I think the frame rate, is acceptable between 30 to 60. So 30, I use a red line, 60, I use a green line. Because 60 is.
Sorry, you can go ahead.
Yeah.
Just make sure.
That's even better. So everything between 30 and 60, I consider it good. So that's why there's a line there.
Any last questions for Charles? Go ahead.
in my simulation, it uses a block as its own calculation. But the email is like home. But also the articulation, even like if you have creativity. So the reason for that, what was that?
So it definitely depends on how many SMs you have, how many cores you have, and stuff like that. And then it also probably depends on what how many points you're doing and stuff like that too. So there's a few different things that can affect it. I wouldn't expect 1024 like chance hard of this graph to increase the FPS by like 40. That seems a bit high. So maybe try it with a different number of points and see if that changes something. Maybe try it from 1,000 points if that's fast enough.
I also test them all on release mode, so I'm not
Yeah,
sure.
you should definitely test everything.
Yeah.
All right. Thanks, John. Good job. So the one thing I'll say is all three of them did a great job on the readmes and stuff. But if I did pick you, doesn't mean you did a bad project or a bad readme. These are generally random based on what looked good in a readme. Like if you had a cool screenshot or a cool graph, I'm like, okay, let's pick this person. So next time I'll pick another group. All right. With that said, recording and everything. So one of the most important parts, like I mentioned in the first lecture, is your readme. This is critical because this is what is the most front-facing thing of your project. You may do the cleverest engineering, the most incredible algorithm that anybody's thought of, but unless your readme is good, nobody's going to read it or understand it. Okay, so here are a few tips that will help you do better readmes in the future. So you've got your hands on project one, which is what you want. And now from project two, you can go back, look at these slides and see how you can improve the readmes. So I think all of you did this to a certain extent. Provide context, contact info, and a representative image. The reason for this is, again, the people who are looking at your readmes are not always GQ engineers. They're HR people, they're recruiters from LinkedIn and wherever else. So you want to give them an idea of what you've done. The other thing you want to do is once you've put your cover short, you want to add more screenshots. Talk about what the pipeline is. Maybe you don't have a pipeline in voids, or maybe you have a pipeline for each different algorithm about having the same number of points and how fast the algorithm runs, something like that. But you want to essentially give them a pipeline of what's happening. And then you want to annotate your images. In this probably becomes really important for project 3 when you do path tracer. You want to annotate what's going on. For us, we look at cornel boxes all day long. The HR people may not. So you want to highlight features for them. So where's the reflection? Where's the diffraction? Where's the caustics? All of those kind of things you want to highlight. Yeah, it adds noise to your image, but you can have it side by side or anything like that as well. So would definitely recommend doing that. Have debug screenshots. These are really cool because they show different ways you've thought about the problem and how you've optimized the problem. So these are from Cheng So Lin's deferred shader back from, I think it's like 2016 maybe. So showing these will help not just the HR people, but also the engineers understand that you've thought through your problem, you understand it, you understand the steps that have allowed you to get there. So it's a really cool thing to show off. Then you want to do side-by-side comparisons for feature improvements. Some of you did it for points where you had different points, different number of points in the scene, but maybe something like this as well, where you're, let's say, adding anti-aliasing to your path tracer, which I expect most of you will do. You want to show them how it makes a difference, and that is really critical. And then probably the most fun part for me, at bloopers, these genuinely add authenticity to your problems and your projects. Showing things like these help people understand that this was work done by you. It's not you've just forked somebody else's project and started something for fun. You've put in the hard work, you've ran into problems, and then you've solved those problems, which is the mark of a true engineer. Engineering is all about running into a problem and figuring it out, right? So you want to do more of these. And then some more bloopers for you. And these are actual bloopers people have shared in their readmes or on Piazza or anywhere else. This was one from Boys. I saw a few people share not as bloopers, but as bugs and problems where forming a sphere and stuff like that. This definitely reminded me of that. Here's another set of bloopers from the rasterizer project we had a few years ago. If you have illusion problems, maybe close your eyes or something. And then this was another one. This was from a path tracer where doesn't get lit up. Everything's black and white. And I mentioned when Charles was doing about the smoke simulation I had. This is mine. This was technically a blooper. Let me go to the right. Yeah, this was technically a blooper, but it looks freaking amazing. At least in my opinion, it's freaking amazing. So can anybody tell me what caused this to happen? It wasn't intentional, and I'm talking about the daily kind of things. Let me go back. So if I pause there, so you can see the blue has the whites and stuff in it. Anybody have a guess on why that might be happening? This is an OpenGL, by the way. It's visualized with OpenGL. You're on the right track, but it's not a floating point error. Yeah, it's not clamped. The colors are not clamped. And there was a bug. It was a mistake. But hey, in my case, it's a feature. So yeah, you want to take advantage of those. So yeah, tips, use bloopers, videos and animated GIFs are good. I mentioned LiveCap there. I should have probably also mentioned Screen to GIF. That's another really cool tool. And if you're using it in Moon Lab, then it doesn't require you to install it. So that can help you out. You want to link to any demos or videos outside of the README, do your performance analysis, build instructions if you've changed anything, and then focus on what you need. You have almost 30 students in this class who are doing the same projects you are. What is unique about what you've done? That's what you want to focus on. Because it's very easy for a recruiter or an HR person to be like, hey, I know CIS 565 students are good. Let me go to one of the projects with the pull request tab and look at all 30 of your projects. And which is what we want. That's the thing, right? So you in your README, you want to differentiate yourself about what you've done in the project. So those are some tips, and then I have a few more. So I mentioned in the last class, or sometime it's okay to look at readings and stuff for inspiration. So here are a few that I've linked out. You definitely you should take a look, whenever you have time or working on your reading. This is a README from Patrick Posey, who used to teach this class before me about how to make an attractive GitHub repo, how to make it clean and all that. So be sure to read this. Now I'm going back to, I think Bowen's comment about spending 4 hours on the README. Generally on average, I think the README is found for maybe between 5 and 20% of every project. I think 20 is definitely on the high side. It's probably 5 to 10. If you think about a project that gives you a week, 10% of a week, if you 24 times 7 is probably somewhere around 160 hours. 10% of 160 hours is 16 hours. So don't you think that might be worth your time to spend 4 hours, 5 hours on your video? It definitely will, because it counts enough for your thing. You're spending that much time on your engineering and problem solving, make sure you're spending a reasonable proportion on your reading as well. Okay? So that, remember that. So some tips on graphs, okay? Let's make this interactive. What makes a good graph? And here I've put an example from Anand's website. So what are some properties of a good graph? Good man. Yeah. Yeah. What else? Good. Colorful, okay. Good. I couldn't hear you, I'm sorry. You should have limits. That's good. What else? Large data set? Yeah, representative data set. You're right. Absolutely. Context is very important. What else? Good. Yes. Absolutely. You want what you want the user to read out of it. What else? Good, my friend. Knowing the audience, yes. So building a graph for an engineer is very different from building a graph for an HR person, for example. Okay, what else? Maybe two more. Okay. You have to choose the right kind of graph. Yes, absolutely. What else? Last one. Good, Ashley. Yeah, the naming stuff. All right. I think you guys did pretty well there. So what's good or bad in these graphs? So the first thing is there's good and bad, but I'm going to highlight this. Label that. If you don't write time there, how am I supposed to know if this is FPS or time? Which are completely inverse of each other. Okay? So you don't know that. Then you want to relate to your bottom axis. Okay? This one doesn't have a bottom axis. How am I supposed to understand what's going on? Right? Like it says number of elements. I don't know if it starts from 0 and goes to 10, or if it starts from 10 million and goes to 100. I don't know anything about it. So you want to number and name it. Okay. And then, Matt, you said this, know your audience. Units and units that are understood by your audience is important. Okay. So let's take these two graphs, for example. In the gray graph, okay, the units are pretty clear, 5,000, 10,000, 20,000, 30,000. It's fairly easy to understand for everybody. Time also easy to understand in milliseconds. Okay. Let's look at the right one. What's wrong with the right graph? What's wrong with the right graph? Good. Yeah. Look at how much of the stack is actually used for maybe 20%. Yeah, most of the space is unused. What else? Good. Maybe, yeah. But maybe not giving on the y-axis. Okay. What else? What's the head over? Units for the reader. Which unit are you right? Units of the reader, right? I think you understand. I think what's the other unit of the chart? Size. What about the size? So the size of that. Exactly. I remember probably in the first class, I was going like 1024 times 256 to blah, blah, blah. And you get like, how do you do it? No. If you ask me 10 power of 12, I will go 10 power of 2 power of 10 is 1024, and then I multiply by 4. That's what I would do. Nobody will know it. But if engineers don't remember these, there's no way an HR person or an average Joe is going to remember these. So you want to numbers and then feel. All right? Graphs. Another important thing about knowing the leader and giving context. Which direction is better? Like the access is big, and it's in a decent unit, final strategy. But humans, or at least in the Western context, left to right is good, top to bottom is better. Like as a line that's going diagonally topward is good. So my assumption would be the yellow and the blue are better than the blue. I put without reading too much, without glancing at the entire or not glancing, I would say blue and yellow better. But if you were just scrolling through the room, you're going to get the wrong information. So when you're designing a chart, you always want to make sure that going right and top is better. Okay? And if it's not, you want to write it very, very clearly. Lower is better. You have to say it. Otherwise people are going to miss it. In this chart, you're getting a completely the wrong information of what you may want to have. And then choose your range. This goes back to what Charles pointed out in the other chart. This chart, again, probably uses 20% of useful information. In GP programming, you know that sizes, by now, you know that sizes less than 1,000 or 10,000 don't even want to go to the GP. So you should choose sizes that start at a decent point. I'm suggesting 256,000 there. But you can start at numbers that fit the problem, but don't start from zero. That's it. Otherwise, you're just wasting space. There was a comment about color. Using color families, especially when you have lots of information, using color families will be really good. So for example, in this Anand spec chart, they have similar colors, not the same, similar colors for the same family of GPUs. For example, the 2080 Founders Edition and the 2080 have very similar colors. Same thing with the 2080 Ti and the 2080 Ti Founders Edition. Because they want to show that these are slight variations on the same card, but generally they're the same family. So if you were to, let's say, take your Boyd's project and put all the runtimes on a single chart with 10,000 and 100,000 points in 3 different algorithms, you have 6 lines, right? 3 different algorithms, 2 sizes, 6 lines. You would use similar colors to denote which lines, which algorithms you are. So that's one example of doing it. So you want to keep that visual, association also going on. These are all subconscious things for us as humans. If things are similar color, we associate them. So you want to keep that going. Any questions about charts? All right. So last thing I have is about promoting your projects. It's already close to 6. How many of you have used social media to promote your own work, or maybe an internship or full-time job that you previously had? Or how many of your potential employers use their social media to promote their work? Probably everyone, right? You follow NVIDIA, you follow AMD, you follow Intel, you follow Facebook, whoever else. They all use some form of social media. And if they're using social media and you join their company, there is a general expectation that you get to use social media and promote the company's work. You are a representative of the company, so you want to be promoting their work. So I flipped the questions around. how many of you have shared your work on social media? One, halfway. Liam has done it. Yeah, so Paul has done it. So what you want to do is more of this. This class is all about putting you front and center so that you're out there, ready to take on the industry. So I'm going to show a few examples. The first one is coincidentally Liam's team. Liam's team in 2018 did the first DXR path tracer in 565. DXR had just come out that year. They killed it with social media. They got so much publicity. So Ziad was Liam's teammate along with Henry. They used social media. They made a blog about it. So they did a series of 3 blogs, which were incredible. And they got retweets from all kinds of industry leaders in DirectX because it had just come out, and the fact that students were using it was incredible. So you want to keep promoting that. There was another one. This was a really cool one, by the way. So this was also, I believe, in 2018. There were 2 students who were doing a fluid simulation based on a paper, a shallow fluid sim, and they were stuck. They were stuck on some problem, but they put it on social media and stuff. And the author, they tagged the author, saw this, and he replied looking good. And then he also emailed them. Is that my next slide? Yeah, that's my next slide. He also emailed them, telling them a better way to do it. Okay, so this is all about promoting and collaborating. Doing something like this, where you're giving credit to the author, is awesome, because you are telling the author that, hey, you may have published this paper and spoken at a conference, but I love your paper and I'm working on it, and that is probably one of the best things an author can get. Okay, so you want to do more of this. You also want to do more publicity and stuff where you're putting your projects out there by yourself. I'll retweet and stuff whenever you want. But then Emily sent this message to Patrick back in the day. An Xbox engineer who contributes heavily to the API saw her project and then contacted her about wanting to talk more about the project, potentially a job and stuff like that. So the more you do this, the more awesome it'll be. Last one, in 2017, Yusuf was a student and then a TA. He was doing a path tracer for Metal, which is Apple's GPU language, right? At that time, there wasn't even a random number generator in Metal that used GPU. So Yusuf and his team did one as a side project. And then this got followed by a couple of engineers who were probably working for Apple at the time. So it's entirely possible that Apple used Yusuf's project in their code. I'm not making any claims, but it may have happened. So there are cool things like that that you can get into. And finally, I've shared my story. This was, you can see the date here, October 17, 2012. That's when I was taking the class. This was a tweet about my Path Tracers blog. The key thing here is seeing this hashtag CUDA. That allowed the company I eventually joined, Arrayfire, to follow me. Because they followed me, I knew they existed. I applied for a job and got it. If this tweet didn't happen, I probably wouldn't have my first job. Maybe I would have another job, but not job, and maybe I wouldn't be teaching here. So yeah, things go in circles. So I know it's scary. I was scared to do this. I probably had maybe 2 followers back then, and probably 2 random people that too. So it's scary, it's difficult, but once you do it the first time, it becomes very easy. You have to get over the inhibition of making it, thinking that, oh, my work is incomplete. There are people doing so much awesome work, in the companies. Maybe you're doing a game engine and you're like, oh, but Unreal Engine is so much better. No, don't get scared about that. You're doing, what is your budget and what is Epic Games' budget? How much time you're putting into it versus how much time is Unity putting into their game engine. Forget about all of that. You are working and your work is awesome. Publicize it, because that's the only way you get to publicize yourself. Okay, so That's my spiel, that's my motivation. I'm encouraging you to do it. At some point, I've considered putting a grade on it, but I don't think that's the right motivation. The right motivation is that this is promoting you and you should be motivated to do it. So that's it. Any questions on readmes, charts, promoting yourself? No. It changes by project. It's usually between the 5 to 10% mark. Any other questions? All right. So maybe Leo, we push it a little bit. Let me get through scan and stuff, and then I'll give it to you for recitation. But these things take long. My timing's completely off. All right. So great stuff on readmes and stuff. Let's get into some algorithms. So today is not necessarily going to be about CUDA. It's not going to be about architectures. It's going to be about algorithms, sort of like we did with matrix multiplication. But we are going to take algorithms that may not be obviously parallel, like matrix multiplication or vector addition is. But you'll see how we can take non-obvious algorithms and then make them parallel to work really well on the GPU. So let's start with an overview of what we do today. So we do parallel reductions, which is the simplest one. Then we'll do scan and stream compaction. These two algorithms are going to be used in project 2, so make sure you pay attention. And then finally, we'll have two of the smaller ones in summed area tables and radix sort. All right, so let's get started with parallel reduction. A reduction is given an array of data, you reduce it to a single value. Okay. For example, this is add all the numbers in an array, or multiply all the numbers in an array, or get the max, or get the min. Okay. So the thing to consider here is the arithmetic intensity, basically compute to memory access ratio, something we spoke about in matrix multiply as well, how much compute we are doing in all the dot products versus how much memory we have to read. So that's an important consideration here. So some examples of this are sum, max, product, average value, all of those kind of things. How are all of these algorithms different? Or how are they the same? Yeah. Yeah, they have to iterate over each element. What else? They generally work on a pair of numbers at a time. At least in the common way of doing it. In the naive way of doing it, you compare two numbers, or you add two numbers and stuff. So what we are going to do is called parallel reduction, because we don't care about serial stuff in this class. We care about parallel. So in parallel reduction, we are going to take that sequential operation and make it parallel so that we can run it on a GPU. So let's see how this works. How would you find the sum of this? The naive way, the CPU way would be 0 plus 1 equals 1, 1 plus 2 equals 3, 3 plus 3 equals 4 or 6, 6 plus 4 equals 10, and so on and so forth. How would we do this on the GPU? You pick the numbers, you add them as pairs simultaneously in parallel. You do it again, and you do it again. Okay. So this is similar to if you've played fantasy basketball at March Madness or something like that, or if you're a soccer fan, you've seen the World Cup. You essentially reduce what is a serial operation, log n, or O of n into log n passes. Okay, and all of these execute in parallel. All right, everybody with me so far? So let's see how this might actually look in terms of pseudocode. I'm not going to write actual code, but pseudocode. So if we have some pseudocode here where D is the depth, okay, or the level of iteration, then what we are doing in the first iteration is have a for loop K for all K. Again, this is not writing this necessarily as CUDA, but for all K means you do it in parallel, okay? So for all K, in the first pass, you're picking K of 0, 2, 4, 6. You write the sums of it. And then you're going to increase D. So you see D is 0 here. Let's make D 1. So once D becomes 1, 2 power D plus 1 becomes 4. This becomes 3. And this becomes 1. So what these numbers are doing, and all of these plug into the equations here, they are your increments, your offsets, which get plugged in there. So once the offsets change, your simplified equation here is x of k plus 3 plus equals x of k plus 1. So you're seeing that offset here. Now you're offsetting by 2. If you compare it to previous slide, the difference between k and k plus 1 is 1. So you're adding adjacent elements. Whereas in this, you're adding alternate elements because now the offset between the left hand and right hand side is 2. And then in the next level, you're again increasing D equals 2. So your offsets are changing. So now you add these values here. So you get your final result. Everybody with me? Any questions? All right. So note the plus equals here. We are doing this in place. We are modifying the array itself. How does this matter or not matter? Sorry, say that again. You don't have any extra memory overhead, so you're overwriting it. What else? Why doesn't it matter that you're overwriting? Good, man. Exactly. You only care about this final number here. You don't really care about everything that's in the middle. So that's the final thing you want. All right. Anybody else have any questions about? Go ahead, Jonas.
I was thinking about the choice of summing two numbers and what's the trade-off between some more and
Yep.
you wouldn't have to go as deep. What do you think about that trade?
You tell me. What do you think happens if you add more numbers per thread? I mean, think of it in the terms of millions of elements. Like for the sake of slide, we're doing 8. But if you think of in the terms of million of elements, you're right that it reduces the number of iterations you have to do. That I agree. What you're forgetting is that the whole point of this is to not do serial addition. So if you're doing 4 additions per thread, you're doing serial addition, whereas we want to do parallel. So you're taking that O of log n that we produced and turning that back into O of n, which doesn't happen. But yes, you do have a point that when you get into the millions of elements and you consider that, remember the first slide that had consider compute to memory access, that's where it could make a difference. Where if you're just doing one operation and the thread is exiting, that's not good enough. You want to do more, just like we did in matrix multiply. You want to do a little bit more, so maybe you do 4 additions or 6 additions. Maybe not. You don't do 128 additions. You do a little bit more, and we'll actually do that in the performance lab. We walk through it, something like that. Okay. Any other questions on reduction? Good, man.
Then for serial, is there a
That's a good question. I mean, I've generally represented these as O of log n in this case, because you're reducing the number of steps. I haven't thought of it that way. For example, a vector addition, if you're doing a vector addition, you're going from O of n, like A plus B equals C, you're going from O of n to O of 1. But if you think of it in parallel algorithms, that's still technically of O of n because you have n threads. So I'm sure there's ways people have represented it, but just because we are in a classroom and we are used to O of n, O of 1, we'll use that. Okay. All right. So if you're good with scan, let's take a look at, or if you're good with reductions, let's take a look at scan, which is the next level after reduction. Basically, it uses reduction. So scans are also called all prefix sums. Okay. These are, and I've given an example here, where you take an array of elements, A0 to AN minus 1. We have a binary operator. Now I've used the symbol to represent any binary operator. And this identity I is important, okay? But I'm representing it as I, it can change. And the output of this array is, start with, of the operation is, you start with I, then you have A operator A1, A operator A1, A2, so all the elements that are essentially coming before it, and then so on and so forth until you get to the last element, okay? So in this case, we don't only care about the single scalar operator, we care about the entire array, okay? Everybody with me in this? Good, Charles. Oh, sorry, not Charles, Richard. Andrew. All right, Andrew. Anybody want to answer that? Why is it I, not 0? Oh, A0. So that is, we'll get to that in a minute, but this is, if I'm jumping a few slides, this is called exclusive. So you don't include the first element. There's another form called inclusive where you do. Okay. All right, so let's look at a couple of examples. If the operator is add, okay, then you take this array here. In addition, identity is 0. Okay, because that doesn't change the operation. So that an identity is what doesn't change the operation. So you start with 0, you put the first element, well, you put the 4 is 3 plus 1, 11 is 3 plus 1 plus 7, 11 again because 0 here won't change that. Then you get 15, which is 3, 1, 7, 0, 4, and so on and so on. So you get this array here. Okay. So it seems sequential, right? Because you're adding them one by one, right? So now let's take this and make it parallel. That's the goal that we're going to go. Mm-hmm. Good catch. Good catch. The slide is wrong. Good catch there. So maybe let me edit it right away so that I don't forget about it. Slideshow from current slide. Okay, this is the right thing. So I-A0. All right. So everybody on board with how we got to this addition? Who can tell me what the identity is of multiplication? One. All right. You guys understand. My job's done for today. All right. So there's two types of scans now. There's an exclusive scan where the first element of the output array is identity. And then there's inclusive scan where the first array of the output element is A0. It's not identity. What's the difference between these two? or how do you visualize, how do you go from one to the other? So what you would do is, if you wanted to go from inclusive scan to exclusive scan, shift all the elements right, and then you insert the final number here. If you wanted to go the other way, or shift everything left and insert the final number. If you wanted to go to inclusive to exclusive, you shift everything, no, inclusive to exclusive. So this way, you're moving all of these elements right, okay? You're moving it right, deleting the final element, and then inserting identity. You go in the opposite direction by shifting everything left. So you get 3, 4, 11 like that. And then you have to insert the final number here. You have to do a reduction, right? The final element of an operation like this is the reduction. Everybody with me? How we did that? So if you want to go from exclusive scan to inclusive scan, okay? So you're removing the 0, so you're shifting everything left. But now you have to insert a 25. How do you get that 25? You do a reduction on the input array and you get a 25. That's how it works. Okay, but we'll do that in an algorithm fashion. Stay here. What we want to start with is how we do. Let's start with an inclusive scan. How we do it, and in a single threaded manner, it's straightforward. You save the first element. Again, this is inclusive, right? Not exclusive. So we are saving that 3. So the first line, you save the first element. You don't want to change that. And then for each output element, you want to add the number before. And look at this condition. Essentially, this implies how many additions you're doing on this output. So you essentially have to do n-1 adds for an array of length n, because that's how it goes. So now the question is, how do we design a parallel algorithm for this? And how many additions is that going to have? Because if it has more additions, then it may or may not be useful for us, at least in the parallel sense, right? So let's look at it. A naive parallel scan actually builds on the reduction, okay? So this, too many arrows, we break it down, but essentially what we're doing is, like reduction, we'll add elements that are adjacent. Then in the next step, we'll change the offset, add those elements, then change the offset, add those elements, and so on and so on, okay? So in this case, is this inclusive or exclusive? Just by looking at this diagram. It's inclusive because you're not changing the first element here. You're not turning that into identity. So it's inclusive. Okay. And then in here, each thread writes one sum and reads 2 values. Again, you're doing A plus B equals C kind of thing. So you're reading 2 values and writing one sum. Okay. So let's see how this works step by step. This is familiar. We had this kind of array for reduction as well. And then we're going to have D equals 1. That's what you're going to start with. And have this formula here to compute our offsets. But that is pseudocode. Let's focus on the diagram. So what we're going to do is we're going to copy the 0 down, inclusive scan. Okay. And then we're going to do copy 0. We add 0 plus 1 into 1. We add 1 plus 2 into 3. 2 plus 3 into that. 3 plus 4. 4 plus 5. 5 plus 6. 6 plus 7. What's unique about what all the steps we did? No, one step higher. What's they all run in parallel, right? They're all independent. Right. So now, so what you do interpret this from and then computation. So that's what you step. Okay, what do we change? So basically, 3 equals 1, 3 equals, right? 3 equals 2. Now, so that is for and this is not and it's good that it's not like it's not obvious. You don't have the first one. But what now? Now, this proves on the side. So 0 and this is 7. And they have a step. Yeah. So these first, and you often have these features, which is so as we have so we're going to have how do you when you are on the yeah. So you one is more than also practically programs because on here what is really good. So what so I think I exciting. Yeah, and the next part, and I will do it. So the second use scan. Is this okay? Some algorithmic complexity. Okay. This is I don't know have yes. But that's fine. What to do? That's what is that's no more and they get the chocolate from so that's you that so that is looking for your number. The question is so we want to make this faster. So laptop is charging. That's charging. That's charging. All right. So we're learning GPU programming. We are not satisfied with good enough. We want 100% optimization, right? So we want to optimize this more. So next, we're going to see what is called the work efficient parallel scan. So in fact, this is parallel scan. Yeah. Now we're going to learn how to do work efficient parallel scan. So this is called a balanced binary tree. Well, binary, right? You've done it at least once, maybe more times, where you have n loops, and then n loops have log n level, and then you have 2 power d nodes. Okay. You might be thinking, what does this have to do with scan? Think about the blues that I highlighted. This is the inverse of that. Or upside down version. So let's see how this is going to help us. Okay. So when level is 0, you have 1 node, level is 1, 2 nodes. So 2 power d nodes at each level. And this is what's important. So in a work efficient parallel scan, we use a binary balance tree in concept. Okay, there's no tree, there's no actual tree on the GPU that you're constructing like you would do on a CPU with nodes and pointers and all that. This is all in memory. So you're going to imagine it to be a tree. And there's 2 steps. It's called, one is called upsweep, and then it's called downsweep. Upsweep is simple. Upsweep is you are doing a parallel reduction in memory, overwriting data. Remember I said in parallel reduction, you only care about the scalar. Well, in our case, when we're doing work efficient parallel scan, we actually care about the whole array, but we want that data. We want that data also coming from parallel reduction. So let's see how that goes. We take our same array here. Imagine this to be upside down. Okay? We are going from source to result upward. Okay? So upstream. So this should be similar to the or familiar to the So because we are taking all of these, adding this, getting the result from here. Okay. Making it look this way, this is probably showing you more of how the memory is going to look after the reduction. Okay. If you imagine the array stored the left child only, okay, of the tree, then the array is the final output. See, this is the input. Okay, the base is the input. The top here is what the memory is going to look after the parallel reduction, because it's saving the intermediate parameters and you're overwriting it to memory. So nothing writes to the 0 then, right? So you save 0. To the first element, you write only the first step, so that memory shows 1. You don't write to all the even elements, so all the even elements stay the same. Then to index 2, you actually write 6 because you're doing this operation also. 6 steps here, and then finally you find 8 in the last step. Everybody repeats like that. Basically, when we do a parallel reduction that's in memory, the final result is the result of the reduction. But when we are doing the work efficient parallel scan, all the intermediate numbers are also important to us. Anybody has a doubt, let me know, because the downsweep step is more complicated. So I want to make sure that you're covered here. All right. So now upsweep, we essentially get this hypothetical. So after the upsweep operation, even your question. No. After the upsweep operation, this is our in-place reduction on the input array. So we are doing it in place. All right. So now we're going to move to downsweep. Downsweep has a couple of rules. Okay. What we're going to do is traverse back down the tree. Again, this is a conceptual tree. It is a 1D array. It is a conceptual tree. So we're going to walk back down. The first thing we're going to do, okay, first rule is set root to 0. What is the root in our tree? Good man. The final result is the root in our tree. Okay, so we're going to set that to 0. And then this, I don't like to write too much text in my PowerPoint, but let's read this carefully and then we'll see how it works. At each pass, a node passes its value to its left child and then sets the right child to the sum of the previous left child's value and its value. I know that's a lot to take in, okay? We've read it. Let's see how that works. Everybody clear on a node passes its value to its left child? Everybody understand that? Because if you understand that, the next part becomes easy. Sorry, go ahead. I don't want to read the entire line because we'll see how it works. Okay, just make sure you understand set root to 0, and node passes its value to its left child. A node passing its value to a left child in this case would mean, for example, 6 passing its value to 1. Okay, we'll see how it works. I have slides enough to cover it. Okay. Here is a pseudocode for you, which you can use for project 2, but I'm not going to walk through that pseudocode. But it's essentially commented out so you can see what's happening. All right. Let's walk through work efficient parallel scan. In the first step, what was the first rule? Set root to 0. You're setting root to 0. Okay. In the next step, which I've highlighted in this box here for you to remember, at each level, left child copy the parent value. Easy enough. Right child add the parent value and the left child value. Okay. So let's see. So 28 got set to 0 in time 0. Okay. Now what we're going to do is for this element, if we take 0, okay, 0 is a root, right? We're going to take 0, copy its value. Look at the right orange arrow. Copy its value to its left child. Again, left child is memory. Okay. If I come back here, remember this tree. Okay. You want to remember this tree. 28, the final element's left child is the middle line. And then you do that. Okay. So let's come back here. So you reset that in 0. And then you copy 0 into this element. And then you do 6 plus 0 into this element. Okay. So technically, in our conceptual tree, the right child is itself. Okay. And the left child is another. That's the key thing to understand. So let's go to another step and see if that can help us. Let's take the 6 now. You copy 6 to its left child. Okay. Take the number that was there before you copied it, because you're overwriting the value, right? If you copy 6 into index, I believe 6, right? If you copy 6 into index 6, you're overwriting 9. So you want to save the 9 and add 9 plus 6 equals 15. Similarly, if you take the element 0, you're copying 0 into index 1 and then adding 1 plus 0 equals 1. Everybody with me, or should I explain it? Go. I was 1, the left child of 0. So again, we are doing a balanced binary tree, right? And we're not making the root the center. The root is the last element. The left child is indexed by 2, if you want to think of it that way, and the right child is itself. It's a 1D array. It's not a pure tree where each index is its own element. You're not doing that. It's a 1D array. The right child of the tree is itself. The left child is index divided by 2. Okay. So in this case, what is the index of 0 here? It's 3. 3. Index of 0 is 3. 0, 1, 2, 3. Okay. Right child of 3 is 3. It's itself. Left child of 3 is divided by 2, 1. So you round down essentially. Similarly, what is the index of 28? 7. 7's right child is itself. Its left child is 7 by 2, so 3. Okay, so that's why you're getting 6 here. The right child of 9 is, again, you have to think of this array as a tree. Okay. A tree that has its left child at n by 2. So in this case, this may not have the left child of this is going to be 4. So if we go to the next step, this is where you see it. So now, again, you take that tree, take element 15, copy 15 to this element, then you add 6 plus 15 equals 21. Take these two elements, 6 goes copy to 6 here, then you add 4 plus 6 equals 10. 1 gets copied here, 2 plus 1 equals 3. And then finally, 0 and 0 doesn't make, like in our example, there'd be zeros, but if you have different numbers, it'd be different. Who's confused? Everyone. Don't worry, this is one I have to do every year. So don't worry. You have a question? Yes. Hmm? You're talking about this step? No, so it becomes this way. You have to, the tree is like left heavy almost. So it's like twisted. So in what we are doing is because we replace 6, okay? 6 gets replaced, right? So we are copying 0 here. Let me go back. Think of the tree in indices, not the numbers here. Okay, the numbers here are values, but the tree is built of indices. Okay. So when we do this, we are copying 0 into index 3. Okay, and the right child of index 7 is 7 itself. So if I let me draw it this way. So I'm going to draw indices. Okay. So this would be 1. And then if I were to draw this, it would be 1, 3, 5, 7. And then this would be, I never get my trees right. This would be 4, 5, 6, 7. Does this make sense? So the right child is itself always. The left child, depending on the depth, is indexed by 2 or a power of 2. You have a question?
Like in your second row, right? But you're operating on the one on the right. So like the number of blocks in the row isn't actually the number of roots at that step. It's twice the number of roots at that step. Because you need
Yeah. Like I'm not doing 1 and I'm not operating on 1 and 9 here, but I'm putting that entire row there so that you can imagine the tree. So you have 0 elements, 2 elements, 4 elements, and so on. So technically, I'm not working on 6 here either, but I'm showing it in my diagram because it's relevant to our problem. So if I were to start again, rule 1 is replace root with 0. Okay, done with that. Now, our first operation is copy root. Okay, so index 7, copy it into index 3, which is the orange arrow. And then the next index 7, you're overwriting index 7 with the old 7 or the old 3 and 7. So you're copying the new value of 7 equals old 3 and 7. Okay, so see how you copy 0 here, And then the new 7 is 6 plus 0. Okay, let's do one more. Let's do 6. So we are in this level now. So this value here is 6. We are copying that into index 5. And then new 7 is the old 5 before copying it over plus 7. So that's why you get 9 plus 6. If you want to think of it the other way, you can think of the copy after. So let's take that 6 example again. 6 and 9, right? So the new 7 is 7 plus 5. And then once you've computed this, copy 7 over. So now if we look at the final row, let's take this 4 and 6, for example. We're copying 6, so this is this 5 here, this 4, 5, 4, 5 here. The result of 5 is 4 plus 5, and then you're copying 5 into 4. Does this make sense? So essentially, the result of the right elements, or the even elements, if you want to call them, is green plus black, and then the orange is the following. Any questions? Yeah. Would you not end up with 2 zeros again? Yes, because this will get you, I believe, an exclusive stamp. Word official, I will get you an exclusive stamp. Right, right. So good question. How do you get it there? Yeah. No. What you would essentially do is, remember 28, store that in the temporary variable, shift the cell left, put 28 up left. So that's how you would get the inclusive. Basically, for those of you who may not have thought Ashley's question, Ashley's asking in this input, we would get 0, 0, right? So we get 2 zeros. And that's intentionally because this is an exclusive scan where the first 0 is from identity and the second 0 is actually the value in the end. Okay? So this identity is always going to be important. For example, if we were doing multiplication, this would be 1 and this would be 0. And the rule here would be replaced with 1. So this technically should be replaced with identity. Now, I'm more than happy to repeat this again. Let me know if you're confused and what part you're confused with. Because this is project 2 here. Good. Yeah. 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 Exactly. Yeah, the intermediaries get the stack. Anything else? Good. The magic is here. So this is all 2 power d. 2 power d will give you the offset. Yeah. So basically you have to do this. But if I try to explain this with numbers, you would will be lost. So that's why I do it this way. But essentially, if you remember this and remember these releases, you should be good enough for it. Any final questions here before I hand it to you? Sorry? Why does the downfield work? Yeah. It's not obvious. What is obvious? Yeah, think about this orange arrow that's popping. Okay. Do you replace the zero and replace with identity, right? If you just follow the orange arrow, that is taking the final element and actually copying the just straight up copy, no operation whatsoever, all the way to the first element. So that way, your identity becomes the first element of the. So that is the start to understanding why it works. And then as you add them up and think of like you have to flip it over and match it, but essentially this works because in this array, you get the sums of all the previous stuff and then whatever missed out. So the difference between reduction and span is how many additions it is, right? How many elements you are adding up. So you do the reduction, and then in the scan, you are essentially adding the elements that you missed out. That's why it works. So, yeah, so what you were saying, right? So we see this. We see how 28 is getting out of the 6. And so that is essentially happening. So that 6 is getting from each other. And then we are adding the 6 and then so instead of doing the reverse in a more complicated manner, but this is actually more efficient and faster to do from an algorithmic perspective. That's because that with reduction to limit off and out. And in the downstream, you have off and out. Remember, one add and one copy. So you have off and spot and off and out. So that essentially is 2 off and 2 off and out. No, this uses the same number of threads as the other one. This uses the threads. But yes, as it goes down, you are using it. Like in reduction, you are using less threads as being people, right? In the downsheet, you're using more threads as people than downsheet. Yeah. Yeah, so what you would do is essentially, because you're overwriting, at each step you would write that memory in, or read the memory of the place you're overwriting and then make sure you write it. So you don't want to get into this. So you may have some flags and stuff. Any other questions? All right. You want to do the last question before we take a break? We can use my laptop. Yeah.
So you have
so copy Visual Studio over and so if you want to escape out.
All right, so project two. So project two is, project two is the least flashy of the projects. It's algorithms, right? So you'll be comparing the runtime, naive, parallel scan, and stream compaction, and the work efficiency. Just to walk through the code a little bit, we have three different main CUDA files that you guys are going to have to worry about. The first one is we implement the CPU version of the stream compaction algorithm. So first we have a scan function, puts in input data, output data, that's I data, O data, and that's just implementing scan on the CPU, which again, like I said, it's add up all the numbers in an array. Compact without scan is stream compaction. We haven't talked about stream compaction yet, but stream compaction uses scan as a pre-processing step to be able to compute the indices. What stream compaction is basically like a filter, or it's like it's used as a filter in practice, where like if you had some sort of condition that you wanted to test for, you have some array of, for example, rays. This is what we're going to use stream compaction for later. And you have an array of these rays, and you want to test which one of them have hit an object. You could use stream compaction to filter the ones that have hit objects out of the stream. That will make sense later after the code. But anyway, that's a better example. Right. So the next two functions do stream compaction. So they will use the scan function to do stream compaction. Well, one of them will and one of them won't. And this is just to benchmark for CPU. This should be very straightforward. Then we have the naive.cu, which is to implement the naive scan algorithm, which is to take the powers of two, not up, sweep down. So you just have the normal stream compaction. And then we have the efficient. We also have a file called thrust.cu, which is for you guys to write a wrapper around the thrust library's implementation of stream compaction to feel bad about how slow your stream compaction is. That's how it ends up being. But it's worthwhile to know how many optimizations you can make. And as well, if you're trying to make a bunch of optimizations for extra credit, to try to have some sort of benchmark to work with. And then in the common.cu file, we have a bunch of helper functions. So kernel maps to Boolean. This is something that you will run before stream compaction, and then you would run scan on this map to Boolean array. Like in JSON example, in order to filter out null values, the kernel map to Boolean would just have some sort of condition like if not null. And then the array that you would run scan on would be a bunch of zeros if it's null and ones if it's not null. We also have like log functions and check errors, performance timing to measure that. So let me check out the code really quick. Yep. Cool. So there we go. As you can see, here's the namespace. This is the kernel map to Boolean. This would be provided, correct? The common.cu. Oh, okay. Okay. Yeah. Oh, sorry. Right. So this is just a kernel that will apply some condition to every element of the array, embarrassingly parallel, as they say. And then this is performance scatter. This is a tough homework to explain before you guys learn about stream compaction. But in a sense, this is something that you'll run after a scan. So you do scan and then scatter, and that is the stream compaction. You have
Here's where you will implement a naive scan, and this is where you will implement the efficiency. Right. Yes, that's a good distinction. You'll write your kernels as well, like outside of these functions, and then you'll call the kernels within them. Yeah, good point. So, any questions? There's not a lot of blue. Cool. Oh, no, there's a name. Yes. Mhm. Oh, hi. Yeah. So to run the CPU scan, the naive scan implementation, and then the efficient scan. Yeah. We're just some test suite and it'll print out the results with the time as well. Mhm. All right. So everyone's favorite part now is the tips. So all of the concepts. Oh, percent on I don't know, the top left, it says auto save. Oh, it's not quite. All right. Tips. I did this when I look back on my stream compaction assignment. So pay attention to this tip like I did. And don't include the CUDA mallocs and CUDA mem copies in your like in between the two calls to start timer and end timer, because we don't really want the mallocs to count as part of like your timing in your analysis. In addition, in terms of like trying to optimize your stream compaction, try to make sure you're using as many threads as is explicitly necessary. I don't want to go into too much more detail about that because that's like the main part of the assignment is to try to optimize stream compaction, but just think along those lines. And another tip I want to add is that when I looked back on my code, I did in between each of my calls to my kernels, when I was like you have the kernel that adds up all of the threads and you loop through that like log times, right? In between all of those kernels, I did extra mem copies. And that was because I didn't know what CUDA device synchronize was. Make sure to synchronize your arrays. If you go to read from a spot that is currently being written to, so kernel calls are asynchronous. So just remember that if you call a kernel in a loop, then the second kernel is going to run at the same time as the first kernel if you don't synchronize. And so you might be reading from memory that's actively being written to. And so that might cause issues. My addition of mem copy was like pseudo synchronized because that'll synchronize, but that's not what you should do.
Saying the following line should be I remember seeing some lines CUDA something synchronized, which is different from the underscore okay, which is saying that hey, the kernel I just called, wait for that to finish before proceed.
Everyone clear?
I have some question on this stuff as now. I just, what is it? I have to make use this, and then I'm open with the Visual Studio. I just don't know what is this SL.
The SLN file?
Yeah. Which will be the solution. Yeah. what I tried is if I don't produce this and it does not compile.
Because you have to use CMake. So CMake is a cross-platform project generation tool. So you can generate make files with it, you can generate solution files with it, whatever system you're on. So we use CMake so that you can generate Visual Studio on the next projects with it and then run it.
So the CMake makes this. If I write the CMake list, I can compile CUDA code without producing. I mean, I just want to know how.
No, you need Visual Studio to compile. You can't compile it directly with CMake. The CMake is not a compiler. CMake is a project generator.
Yeah, if I make it.
Yeah, if you use the make file, then CMake and make file are different. CMake can generate a make file. CMake can generate a make file.
Yeah.
But CMake and make file are different.
Yeah, what I mean is I use CMake to produce the make file.
Yeah.
Then I can make it without the.
On Linux, yes.
I was a little confused about the last thing you said. You mentioned calling multiple files in a row.
Mhm.
They're not like in the last project, we crawled a whole bunch of files in a row. And technically,
So let me add something. So essentially, CUDA API, all CUDA APIs are technically asynchronous in the sense that they're both asynchronous related to the host, which means if you call a CUDA API, then do I equals A plus B, then I equals A plus B can execute before the CUDA API is finished. Okay, that's one thing. The second thing is CUDA API, and yeah, this is 3-4 lectures later, can be asynchronous to that. You can have different streams of CUDA API. So that doesn't really matter here because we are using the default stream for everything, so relative to each other, all the kernels should be sequential. But for performance testing, you should still call a device.
so there's a concept of streams that we haven't done.
Yeah.
The last one where they were synchronous.
They were sequential, they weren't synchronous.
So the kernels that we were calling on the last one were running at the same time.
No, they were running one after the other. So, but not one after the other related. So basically, if you had, remind me, you probably had something like kernel A, kernel B. When you call kernel A, it's going to tell CUDA to run kernel A on the GPU. But on the host, before kernel A finishes, it's going to tell the GPU, okay, you have to run kernel B as well. But the GPU is going to say, okay, these are both on the default stream. So I'm going to wait for kernel A to finish and then run kernel B. But on the host side, the host code is not going to wait for kernel A and kernel B to finish. That's why you need a CUDA device. It's just going to go to the next step, whatever it was. So if you were to do some of the operation that, let's say you did a CUDA free, for example, on one of those buffers, you would get invalid memory usage.
So on the host, it's just going to rip right through the code.
Yeah, until you call it device.
Okay, but on the GPU, because they're all in the same stream, which is a concept we haven't learned, yeah, they actually do get run synchronous.
Okay, sequence.
Say again, scanner?
Scatter.
Scatter. I think Shizan is going to
Yeah,
talk
I'll
about
cover
scatter.
that. All right. Any other questions? And we can stream them back right after the break. Any other questions? All right, so let's take a 5-minute break and come back around 7:12. Okay. And then we'll go back. Go ahead. did you look at
I was gonna say, you're in your background.
Oh, my background. Yes, what is-
Yes.
Yeah, that's what
I thought classes that I thought maybe.
Oh, no. Not that. Maybe someday. I'll be sure to invite you for right.
So.
Or maybe you guys can buy one and invite me for right.
In the, Insight Impossible thing, for this homework.
Don't worry, you guys will learn Insight very easily with the next one.
with this homework,
Yeah, because this is all numbers, right? And it's all 1D arrays. You guys will love it. So go ahead with your question.
my question is, 90-second video
Mhm.
where you are running the completed code, but not showing us the code, just running it, and you have insight of, and you're saying, hey, these are a couple things in here you should care about.
Okay, let me try to do that on Monday.
Yeah, I mean, just if it's convenient.
Yeah.
At least that would be a starting point.
Okay, I'll try that. Or Liam, if you want to take that on, more than happy to go to you.
That's a
I-
big ask.
Let me know if you can fit it.
Not great. So I don't know necessarily if I'm concerned.
All right, we'll try to figure
So
something
like,
out.
if you send me a good
Yeah.
with like some shared memory application.
Yeah.
You're gonna see like 90% of the time. Yeah, right now I just.
Yeah.
For the final project of this course,
Mhm.
so I'm a PhD student working for
Mhm.
Rahul,
Yeah.
Narayan.
Yeah.
So we have a publishable project that may use my knowledge during this course. I want to do it for the final project.
Yeah,
if
so-
it's okay.
So you are allowed to. I'll go over final project at some point in the semester before you get to the final projects. But essentially, the rules are the work you do in this class shouldn't be double dipping, which
No.
means you shouldn't get a grade for it in another
No.
course.
It's like
and this
a
course.
research. project.
Yeah, so the work you do in this class, let's say you're implementing a new kernel that can then be used in that project, perfectly acceptable as long as it's not double dipping.
Okay. It's like a for a paper.
Yeah,
Or- Okay, and is it okay that's not open source?
Yes,
Okay.
as long as it's accessible to us, that's all.
Yeah, that's. Thank you.
Okay.
Yeah, so basically like I'm gonna graduate next December.
Okay.
That's why I joined in this program.
Mhm. Depends on the company and the industry, but let's talk after class. Yeah. I don't think that's a question. Yeah, that's a statement.
And this stuff is really cool. Sorry, I don't dislike, I hate this. And I'm used to like civilized like, containers stuff. And so I'm wondering, like, Python has a recent CUDA library. but
Which basically uses C, yeah.
it's fine. I'm wondering, like, how, does anyone containerize this stuff? And, like,
So-
code doesn't have
Yeah, so there are two things, right? The one, yeah. The one thing is, the first thing is you need the hardware, so it's not necessarily, even if you were to write Dockers and stuff, you still need, now then you run into the issue of, okay, how do you virtualize the Docker so that the Docker has access to the GPU? Okay, so that's one issue. The other issue becomes, now I get your frustration with Visual Studio. Sometimes it's great, sometimes it's not. But I think as you go on and learn, which admittedly most university courses don't teach you how to use debuggers, you get used to it and you love it. You like later on through the semester, you're like, oh my God, like why haven't I used debuggers in previous classes? So even if you were to use Python or Docker or anything, ultimately you need the tools to be able to debug. And those may or may not exist for the other languages, because all of this is natively in C. And then for Python and stuff, you're getting wrappers. Yeah. Basically, yeah, that's what would happen. Like, even on the cloud, you have a CPU, GPU architecture. You're not getting away from that. So you would still need host code and device code, and then around that host code, you have APIs to call whatever function that then run on the GPU. So that is how, for example, if you were to think about Google Stadia or Xbox Cloud or whatever else, NVIDIA GeForce, whatever they call it, those are all big servers running in some cloud somewhere that have a GPU that are rendering the game on the GPU and then streaming the pixels down to you with some interactivity. Yeah. 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 Maybe. So the CPU versions that you write can be unoptimized as you want. If there is an easy enough library that you can integrate without breaking CMake and stuff and making sure that we can compile it, I don't mind, because there's not a CPU class, it's a GPU class, right? So if you want to use a reference implementation for CPU, I'm fine with it. We want you to do the CPU implementation so that you understand the algorithm. Okay, that's the main goal of it. It's not to optimize the CPU implementation. Yeah. All right. So shall we? Yeah, go ahead.
There's nothing stopping you from adding this.
Yeah. So you can have naive CPU and naive third-party library, whatever you want. All right. So let's look at stream compaction, which is really your homework. So like Liam said, stream compaction is given an array of elements, create a new array that has the elements that meet a certain criteria. Okay. And the important thing here is that we have to preserve the order. Okay. That is the key thing. So in this example, what would our output array be? If you're saying we want all the green elements, what is our output? Right. ACDG, you're right. So you guys get stream compaction. So the uses of stream compaction are plenty. Like this list doesn't even cover it. So path spacing, for example, if your grays go out of the scene or invalid, you remove them. Collision detection, they don't detect a collision, remove them. Sparse matrix compression is another one. You don't want to use the zeros, so you want to remove them. So again, that way, so essentially, it reduces how much work you have to do between the CPU and the GPU. So let's see how to do stream compaction. Okay. First, we're going to compute a temporary array. This is your, what was the function name? Map to Boolean or something. So you're going to map to Boolean. We said we want all the green elements, right? So if it's green, we put 1. If it's 0, we put, or if it's red, we put 0. That's our condition. This is not overwriting. This is a new array itself. So A is green, so 1. B is red, so 0. And so on. You fill the array. Everybody clear? What kind of a problem is this? Embarrassingly parallel. You're catching on. You can do all of these in parallel, so you get everything at once. Simple. This is probably the easiest kernel you're going to write all semester. Okay. The next step is to run our friend scan. Okay, so what is the result? And you're going to run the scan on the Boolean array here, and assuming the Boolean array is integer. Okay, so what is the result of scan? You get an exclusive scan. So exclusive scan means first element is what? 0. Okay, and then 0. Then what would the first element be? 1. Second element is 1. Third element is 2. All right, you guys know. So I'm going to skip. So this is the scan. Okay. So scan also runs in parallel. So you're going to write a kernel for scan, and you're going to get the scan result. All right. What can we do with the scan result now? Go ahead. Yeah, exactly. The final number here can represent how many true values there are. And I say can because I'll come to it. So step 3 is now called scatter. This is your scatter kernel in your GPU implementation in project 2. In scatter, what you're going to do is take the result. The result of scan is the index into the final array. Okay, remember that. Result of scan is the index. And you only write it if the Boolean is 1. Okay, so let's see. A Boolean is 1. Scan index is 0. So A gets written into 0. All right. We skip B. B's Boolean is 0, so we don't even care. So skip B. C Boolean is 1. What is the index with C? 1. So you write C to 1. Then we come to D. D is true. We want to write it. What's the index? 2. So D gets written to 2. And then we skip E and F. So we come to G. G's index is 3. So we get that. And then we don't have to do H. Okay. Everybody clear on this? Go ahead, Stephen.
Like we're using an additional buffer to like have the like Boolean array.
Yep.
And then we would need an additional buffer so the scan would modify it.
Yes.
So you would have 3 buffers.
Exactly. So in this case, what you want to do is remember how scan was writing it in place because of the reduction we were doing. You would take the source, make a copy of it, memcopy device to device, remember? And then you would run the scan on the copy. You shouldn't modify the source itself. All right. Any other questions? This is parallel. So runs in parallel because technically writing A1 to 0 is completely independent of all the other elements. So
Final, that's how we know there are 4 elements.
right. Yeah. Go ahead. Sorry, say that again. No, it won't. And I'll come to that. Because if you had H as green, this would be 1. This would be 4. So you would write 4. Your length would be 5. So this, I remember I said scan result can tell you the array size. It won't always tell you. So that's where you would have, if H were 1, you would have a 5th memory here, and you would write H to index 4. Okay. All right. So this runs in parallel because writing A to 0, C to 1, D to 2, and G to 3 is completely parallel. They don't collide with each other, so it's completely in parallel. So that's your scatter kernel. And that's all stream compaction is. I don't have any more slides on stream compaction. If you understand that, you understand stream compaction. Step 1 is compute the Boolean array, probably the simplest kernel, right? Step 2 is run scan, which I know is a big complex thing, but I'm simplifying it. And then step 3 is scatter, which is the simple operation here where you're using an index from another array to use if and then write. Good, Rachel. What would happen if you used inclusive? Right, so the first number is going to end up being 1. So you wouldn't have A gets written to 1 here, right? So that's why you want the first true to always be on index 0. So that's why you use exclusive scan, not inclusive scan. Right. Good point. Good point. We still need scan because we need scan for where to write the output because the order matters. Remember, the order matters. That's why we need scan to know the index. However, as you do scan, you'll do a reduction in the upsweep step. In the work efficient, you do an upsweep, so you do the reduction. That reduction is going to tell you how much memory you have to write to the output. This scan may or may not tell you how many elements you need, but the reduction you do as part of the scan will always tell you how many elements you need. Okay, so that is the distinction. Yeah, go ahead, Jonas.
So I'm just noticing that, so what we just said, was wherever there's a 1,
Yep.
you are gonna look at the blue and just copy. I mean, that's the index of,
Yeah.
But like if you look at, it seems like every time, if you just look at the scan result, the numbers, whenever the number changes, like jumps from 3 to 4,
Yep.
that's where the 1.
Yep.
So is there any?
That's happening. You're going result to thesis, but the thesis is that this jump is happening because 3 plus 1 equals 4.
Right, but from like a memory standpoint, is it wiser to go back and look at the 1 or the mustard array, or should we just check the next element and see if it's different?
I mean, why would you use a branching condition and more global memory ease when you have the simple array available to you, which is already computed, because that's what's giving you the scan anyway.
You're just saying that you wouldn't need to allocate a new buffer because it's almost array in place.
Oh, okay.
Scatter, you can just look at the next.
Yeah, technically you could, but you're wasting a lot of branching conditions. Then because within a what, some are going to be true, some are going to be false. So you're getting into a branching condition which you don't want.
And it's both, like, say, for C and D are both going to check its value. And then that's, like I don't know, have we talked about length conflicts and stuff?
No, we haven't talked about
Okay.
so yes, that you could technically do it, but it's not going to be more optimized than this version. Any other questions on stream compaction? So basically the goal of project 2 is to get you guys understanding how parallel algorithms work, help you get used to Nsight, get used to the profiler. And then if your stream compaction is fast enough, and in some cases faster than Thrust, because Thrust has a stream compaction, you could use your own stream compaction in your path tracer. If you don't get a great stream compaction, that's fine, you can use Thrust. But the goal is, if you're able to optimize the hell out of it, you can use your stream compaction in path tracer, which will be faster.
We know that we can utilize the shared memory.
Yeah, so that's in the extra credits and stuff. So yeah, shared memory, there are optimizations that you can do for extra credit. But I'm pretty sure it does. No, a lot of students have. The thing you have to remember is Thrust because Trust adds templates and whatnot, and it's a header only library, you could get better performance than Trust. It's not impossible. Any other questions before I move on to the next version, next algorithm? All right. So let's look at summed area tables. Summed area tables are simple. It's a 2D table where you're adding elements both in X and Y axis. I'm not going to read that entire statement. So for example, if this were our input, like an input image, the result of index 2,2 will be the sum of all the elements bottom left of it, if you think of it, or indices that are less than that. So in this case, you're adding up 0, 1, 2, 1, 2, 1, 1, 1, so you get a result of 9. Okay. So the use of summed area tables is for things like filters. So where you can do various kinds of filters using summed area tables. Again, a very parallel operation, right? So one example of this is adding a depth of field, which uses summed area tables to create that buffer effect or blurring effect. So let's see how we can do summed area tables. So if we have an input image that's here, how do we get the summed area table? Let's do it manually first. Let's do it. Just read it out. 1 becomes 1. Okay. What's next? What is the result of this element here? 2. Again 2. And then 4. Everybody follow? What's next? What's the result here? That's 2 again, because you're adding 1 and 1. What's the result here? 5, because you're adding 1, 1, 1, and 2. And so on, and so on. So now you can fill the whole thing up. You get 12 and you get 14. So how do you implement this on the GPU? I'm pretty sure you guys know the answer there. Sorry? I mean, thread indexes you have to use, but how would you actually do this? How do you do it in an optimized way? And without 14 having to read the entire matrix. Stephen? I knew somebody knew the answer. You do inclusive scan. You do first inclusive scan on each row. Okay. So this is the result of an inclusive scan on each row. Make sure you verify it. And then you do inclusive scan on each column. And you get a summed area table. That's it. All right. So we're okay on time, I think. Okay, we can get through radix sort. All right. So radix sort. This is different from everything else we've done before. Okay. So this is actually sorting and doing stuff on bits. Okay. So stay with me. So radix sort is really efficient for small sort keys. And keys and radix sort are the number of bits. Okay, radix sort works on bits. So if you have k bits, then you require k passes. For example, an integer has 32 bits, so you need 32 passes. Okay. The rules in radix sort are that each radix sort partitions the input based on 1 bit. Okay, based from LSB to MSB, it's going to work on 1 bit. So let's see how this works. This was our example. Anybody want to give me the numbers here? The integer values here? So we have 4, 7, 2, 5, 6. Yeah, 6, 3, 5. All right, you guys know your binary bits. All right. So in the first pass, what we're going to do is move all the least significant bits. Everywhere that is least significant bit is 0, we are going to move it left. And anywhere the least significant bit is 1, we're going to move it right. All right. So let's look at this. See the bolded values. 0, 0, 0, 0, 1, 1, 1, 1. Everybody follow? What happens in the next pass? What are we going to do? We're going to use the second least significant bit and do the same thing. Now, it doesn't matter what the first most significant bit or least significant bit was, we don't care. We only work on the middle bit. So now I can look at the bolded values, 0, 0, 0, 0, 1, 1, 1, 1. And I remember I told you the least significant bit doesn't matter. So see how you have 0, 0, 1, 1, 0, 0, 1, 1. But
like the moving it around now.
yes, how do you do that? I mean, we did that in stream compaction, didn't we? We maintained order. So yes, you can maintain order through radix sort. So now what are we doing? Now we're going to do the third bit. So now we get 0, 0, 0, 0, 1, 1, 1, 1. That's it. That's a radix sort. At least in a small version. If you had 32 bits, you'd be doing 32 iterations of these. So the completed version of integers is this. So now we did it manually, but where is the parallelism? Right, that's the key question. How are we going to do this in parallel? Doing it on CPU and checking adding a bunch of if conditions is easy. How do we do it in parallel so that we are optimizing? Okay. So this is what we're going to do. We're going to break up the input array. Again, inputs can be millions of arrays, so we're going to break it up so that each tile can fit into the shared memory. Okay. So again, going back to the matrix multiplication concept, where the amount of shared memory is important. Then within each tile, we sort using radix sort, using the bits. So you do this within tiles, and then you merge the pairs using a parallel bitonic merge, and we'll show you how this works. Okay. So where is the parallelism? It is in each tile because you're doing it in parallel within the tile. And then where is the parallelism within each tile? Because you can do each pass in sequence after the other pass. So we can't change that. That sequence is sequential. But can we parallelize individual pass? Yes. And we'll discuss how. And then the merge is also parallel. So let's see how that goes. So what we're gonna call this kernel a split. Okay. So follow me here. Okay. So for array, I at n pass n. Okay. So let's say 0. You compute b, which is a true or false of bit n. Like a stream compaction, except we're not compacting it, we're just computing the Boolean array. So we are saying if the least significant bit is 0, you write a 0. If the least significant bit is 1, you write a 1. So Boolean array, B. Then the output array with the false keys before the true keys. So this is where we are going to do the parallels, okay? So step 1, we are going to call it, so we have computed the B array, Boolean array, everybody clear on that? If the bit we are computing in that pass is 0, we write 0. If it's 1, we write 1. B array is easy. E array is probably easier, not B. Okay? And then you're going to do the F array. The F array is, what is it? The E array is a scan. Which type of scan? Exclusive scan. Perfect. So the F array is an exclusive scan that is going to store the address of where to write the false keys. Remember what I said. F array is where you write the false keys, not the true keys, the false keys only. And then to calculate the total number of falses, we have this formula. E of n minus 1, where the last element plus f of n minus 1 gives you the total number of falses. Now, in our example here, because it's sequential, you have 4 trues and 4 falses. That may not always be true. You can have many more trues and many more falses. So using this is going to be important because you need to know where to start the true keys, okay? All right, everybody follow me so far. Any questions? It's like stream compaction, but we're not compacting it. I mean, yeah, if you think of it, you're not compacting the memory, you're compacting the elements. Yes. So for basically you would take this and your stream compaction would be like the first half of the array. Yes. All right. So if you know the F array, what do you think the T array is? Here is the true array. So how are you going to compute that? You're going to compute this using this simple formula, which is compute the total number of falses that we had from this equation, and then offset it by that, and then add wherever you have a 1. So you get 4, 4, 5, because that's a 1 there, and so on. So now the T array is the indices of where you're going to write the true values. Everybody follow? So now the final step let me make sure not to put this charge. All right, so the final step is then this simple condition. The device array or the output array is B true? If B is not true, then T of I or F of I. This is giving you the index. Okay, so D array is the final output index array, which is if it's B is true, use the true array, or if it's false, use the false array. Basically combining F and T and F. So you get 0, you get 4, 1, and so on. So you see how all of these are unique now. There's no duplicates. So now all you have to do is take the input, and this is your output input. So I array, B array, mix it up, your output. That is one pass. Okay, that is not n passes. That is not your final result. That's one pass. All right. So given k bits, how do we sort using a new split function? So if we go back, remember how this is working on 1 bit each? So you want to change that, and then you'll get the values. So once each tile is sorted, so you're still working within a block, right? So if you've sorted your block, now you need to sort with all the other blocks. Just because one block is sorted doesn't mean the entire array is sorted. Okay, so we need to use bitonic sort for that. So let's revisit scan for a minute. So as Rachel pointed out earlier, it requires a power of 2 length. So you have to pad when needed. And it also, the algorithm we discussed executes one block. We didn't discuss how you scan across blocks. So let's see how that works. So let's say this input and our block size is 3 for the sake of power. Okay. So you're going to divide it into blocks. Okay. You run parallel over each SM. Everybody follow me so far? This step is scanned within the block, which is easy to do. What you're then going to do is take all the final elements of each array, because that gives you the offset, and you're going to put it into a new global memory array. Okay. Once you do the new global memory array, do an exclusive scan on it, because that will give you the total offset across all the blocks, and then you add it up. So again, within each block, you do a scan. That scan gives you the final sum within the block. So for the first block, going to the second block is easy because it's just 3. But for block 3, you have to add 21 plus 12 plus 3 to get the final thing. So you're going to take the block sums, do scan on it with the block increments, and then you add whatever the color is, you add that as an offset to the scan. So, it's a block, that's too much to put in one class. Right. So, for example, let's say you have a billion elements. Okay? A billion elements, and let's say we have 1024 threads per block. How many block sums do we have? We have a million blocks, right? A billion divided by 1024 is a million. If there were million block sums, that also isn't going to fit in the one block. Do another block sum on it. Then you get a million blocks, do a kernel on it with 1024 threads, you get 1024 block elements. Then you can do it on the CPU because it's small enough. You don't want to do a million elements block sum on the CPU. So you have to sometimes do it hybrid. You have to do multiple steps to get the actual blocks. So this is going to be important when you do stream compaction, because your stream compaction is going to be about for many blocks. So when you're implementing your scan, you want to take this into account. Good. The block increments are exclusive scan and block. So if we go back here, exclusive scan and block sum. You're doing the sum, right? If you do the sum and every block, let's say is 12, the first block offset is 0 because it's always exclusive scan. The next block is going to be 12. Then it's going to be 12 plus 10, 12 plus 12 plus 12, and so on. So you're adding the block sums of the previous block, all the previous blocks together. That's why students scan on the block sums. Let me start. So think of these as bigger blocks, 200 elements. They all have some value that is the final element of the scan. Now, in this example, all of them are easy, because my input was 1 to 12, right? 0 to 10. But in your example, you may have random numbers. The block sum of block 1 may not be greater than block 2. It could be less. So what happens is when you do the block sums and then do the block increment, this is essentially the sum of all the elements in all the blocks before.
So if we take 15 for example, which is the offset we are adding to block 2, it starts here, right? So 15 plus 0. What is the sum of 0 to 5? 15, right? So block 2 needs to start from 15 plus 6, 15 plus 7, 15 plus 8, and so on. That's because you're trying to do a scan on the entire array. So you're computing what is the sum offset of block 2. Because you can compute the scan between blocks, and then you have to add to each element here, all the sum of these. That's what it's done. Because you're adding all the previous elements to each element. So that's why you have to do this block.
Again, we use this in trajectory. Like Rachel had asked before, if it's a non-power of 2, you will essentially pad with identity so that it's always a power of 2. So that's all for today's lecture.
So this is scan. So this scan is used for multi-block scan, and then if we come back to radix sort, which are kind of expressed in memory. So I don't think this is sorted after one step, or at least within the block, and then you have to do this across blocks, and then you also have to do a merge, just like we did with the scan. So let me make sure I have that correct. I'm doing my notes. So merge requires a recursive merge sort to combine two sorted tiles. Now I think there's the slides don't go into bitonic sort because I think that is generally easily parallelized. For example, you can use trust or something for that. And then you need, if you have B number of tiles, and these are in the slide notes, so you can check it out. If you have B number of tiles, then you need log B number of steps. That's blocks to do the bitonic sort, the bitonic merge sort. The first step, B by 2 merges in parallel, and then second step is B by 4, so that merges 2n to 4n and so on. Radix sort isn't in project 2, so that's why I don't cover it in too much detail, but it's covered here so that you understand how it's not just scans and reductions, but even sorting can be done on the GPU. Not completely. There's a few notes around how you do the merge in the slide notes. Yeah, the details are also available in the books. GPU gems and the other one, massive parallel programming. Oh, good. Okay. No, right? Yeah, go ahead.
you use less steps. The number of iterations you have to go through, because so look at this. In work efficient family plan, upsweep is off and adds, because that's just reduction. And then in the downsweep you have off and adds and off and swaps, which in algorithmic complexity is just off and right. Whereas yeah, but it's also faster because if you look at this line, this is you're doing way more addition and also wasting a bunch of things. Like
So I want to talk about the interactions.
yeah. Hold on, let me see if anybody has any questions.
Okay.
So yeah, I don't know your name, so
Lindsay.
Lindsay. Yeah.
Sorry. My project
Zero.
zero.
Trash.
Yeah,
Yeah, I have to take a look. I haven't got it.
yeah. If you have time, or like I know it's like past. I just wanted to like.
Yeah, I know, I know. You definitely should know why it's crashing. I just haven't had the time to take a look and see. So I'll try to take a look as soon as I have time or during office hours. No problem.